In this lecture, I want to bring some closure to the hyperbolic filling story that we started. This is kind of a premature ending to that, but given how technical the nature of the whole story is, I wasn't sure if you have been following or you find the topic relevant to what you're doing. So I will leave you to the amazing resources where it has been written down with all details and in beautiful exposition. And that's why maybe this is a good place to end here. This G is not complete, so we take the metric completion and then we take the original graph out of it. So we talk about the boundary of G, and with this distance of course also applies to the boundary, makes it a metric space, and with that distance it's quasi-symmetric to the original space X. Now, the beautiful work of Carrasco from 2013, I will show that paper in a second, and characterizes basically all the possible ways you can choose this pi, not necessarily of this form, so that you still get a quasi-symmetric copy of X. So what are conditions on the function pi for which this happens? So to understand at least the basics of this theorem of Carrasco, let me introduce some, but I promise not all, of the notation. You assign a value to every single vertex as before, some value between 0 and 1, and this time it doesn't have to be the same for the vertices from the same level. It can be different. So you keep assigning one real number to each vertex. But this is not going to be our function in the definition of the length. What we do is for every vertex down here, let me call this W, you assign this by finding by choosing, not finding. There are possibly many vertical paths all the way to the original root. So you assign pi of W to be the multiplication of the row values of all the indices you meet along the way. And this is up to a choice, of course, but for each vertex you fix one such vertical path. I could go this way, but I didn't, and you assign this pi value. Now you have a pi function defined on each vertex, pi of v1, and here you have pi of v2, and on the edge you just linearly join them. So there is a simple linear function which starts with one value here and ends up with another here. Remember, each segment is identified with the 0, 1. Now you have a pi function defined on all of your graph, vertices and edges. And remember, rho was between 0 and 1, so this pi is actually very small as you go down because you keep multiplying. For example, if rho is a constant function, in our previous example, this would be alpha to minus 1, and then pi would be alpha to minus n at level n, because you multiply n of these to reach there. Okay, what Carrasco does in this quite significant result, he characterizes all the possible choices for pi, equivalently for rows, so that the resulting metric, which is infimum of pi length of all gamma that join V to W, so this would define the distance between V and W. So it gives us conditions necessary and basically sufficient and basically necessary, so that there's also H3 and H4, so that this metric when put on the boundary of the graph becomes quasi-symmetric to the metric space that you start with. And let's have a look at some of these conditions. For instance, this condition says that rho is away from 0 and 1. So there is a lower bound and upper bound. The next H2 condition says that the choice of this pi would not have been too different if we took any different path, because we assume, remember these are assumptions, we assume that if you fix one vertex, and no matter which one of these vertical paths to the root you choose, the multiplication would have been comparable. So this multiplication would have been comparable to the other one if you have two different vertical paths. Therefore, this choice of pi was inessential, basically. And then third and fourth are a bit more technical. I skipped them, but here is the thing, that if you have a row with its associated pi satisfying all of these h1 through h4, then that becomes, the new metric becomes quasi-symmetric to original xd, and that it is Alfors P regular. And this is where it says it's basically necessary because under some more restrictions on the parameters in the construction of the hyperbolic filling, every quasi-symmetric metric on X is by Lipschitz equivalent to some metric which arises this way. So this basically translates all the quasi-symmetric information about a compact doubling connected space into this graph and the functions, certain functions on the vertices. And from there, for instance, you can compute the quasi-symmetric conformal dimension of the space by looking at some combinatorial modulus of the graph. That was the message of the paper, the expository paper. Actually, this is again a result of Carrasco that we did with my collaborators. If you are interested in the calculation of the quasi-symmetric modulus, then of course our rewriting of Carrasco's result is here. So you can find this on arXiv, but it is not yet published. It's being refereed. And let me show you the original paper. So this is Carrasco Piaggio. Basically, this was his work on his PhD on the conformal gauge of a compact metric space, 2013. And the rewriting of that very theorem I showed you is here in Shamma-Gullingham's work on Carrasco's theorem characterizing quasi-symmetric maps from compact doubling spaces to Alfors regular spaces, 2023. Have a good one, and thank you for watching.